All right, in this lecture, we are going to talk about decoders. Pretty important combinatorial logic design block in computer design. You need this a lot of places. So decoders. And we'll talk about encoders as well, which is a counterpart of decoders. So a decoder. So the first one is a decoder. The second one will be the encoder. Okay, it's going backwards. And a logic block for a decoder looks like this. This is called a, you have two inputs and four output. It's a 2 to 4 decoder because it's two inputs and four outputs. Okay, you have A and B, and you have four outputs. Depends on whatever you want to deliver to the output. But you have totally four combinations for the two inputs: 0, 0, 0, 1, 1, 0, 1, 1. Right. So all these combinations can pick up whatever you're going to deliver to the outputs at the same time. So the very standard decoder is like that. It's shifting a one from the first one to the next all the time for every time. So actually, you are shifting one in the very beginning is here, then you shift it to here, then shift it to here, shift it to here. So totally four types of outputs for the decoder. So four options for the inputs first, and then for the output, you actually have four pins. Okay, so the first one will give a 1 here, and the second one will give a 1 here. The third one will shift the 1 to this location and then this location. Right, so again, it doesn't matter. It doesn't have to be 1, 0, 0. This is just one type of decoder you are trying to turn on. So for example, you have an LED here, right? You can turn on every one by one. It's like a running LED. Since you are turning on one every time and you are shifting that one every time. However, you can imagine that you don't have to just have one logic high here. You can have any kind of logic pattern over here, but you have four options to. So actually, since you have 2 bits for the inputs, so that's why you have four types of patterns you want to define for the 4-bit output. It doesn't have to be like that. But this is very standard decoder. We're just having one logic high in the 4 bits. So we are shifting that. This is one of the, it's one standard decoder I want to introduce to you in the very beginning, right? And now since you have 4 outputs, that's why we need to look at every single output to get the logic expression individually. So for example, Q0, so what is Q0? For this column, that's only one here, right? So it's going to be A not B not. Q1 is A not B. Q2 is A B not. Q3 is AB, right? And then, so what's the circuit looks like? You know, we have A, we have A not, we have B, we have B not, right? They are signal lines, and A not is the inverted version of A, B not is the inverted version of B. And so we can get A not B not, and so here's Q0, A not B, A B not. Oh, Q2, sorry. AB, which is Q3. And you're done. That's a 2 to 4 decoder. That's it. And keep in mind, so you doesn't have to be this pattern for every output. You can have any pattern over there, but the limitation is since you only have 2 inputs, so that's why you can only have 4 patterns totally. It doesn't have to be like that, only one logic high here and being shifted to the next digit. It can be any pattern, but only 4 at one time for this decoder, since you only have 2 inputs here. All right. So that's the decoder. So the counterpart for the decoder is encoder, which is going backwards. And let's make a 4 to 2 encoder. Right, 1, 2, 3, 4, and 2. So we have Q0, Q1, Q2, Q3, and we have A, B, just going backwards. And now the truth table looks like Q0, Q1, Q2, Q3 as the inputs, and A and B are the output. So essentially, you can design the pattern by yourself, whatever input, and can give you whatever kind of output. After you design them in the truth table, then you can get a logic circuit using logic gates correspondingly. So now let's just use the same pattern here. Right, and so for this pattern we are getting 0, 0. For this pattern we are getting 0, 1, 1, 0, 1, 1. Okay. Now so what is A? For this truth table, what's the logic circuit? What's the logic function for A? So it is Q0, Q1 bar, Q2 bar, Q3 bar. No, not that one. I'm sorry. So for A, you are having this one, right? So they are ones here. So it's not this. Sorry for that. So it's going to be Q0 bar, Q1 bar, Q2, Q3, right? That's Q3 bar. Almost I make a mistake again. And for B is Q0 bar, Q1 bar, Q2 bar, Q3. Right? That's it. That's a circuit for this truth table. That's an encoder. And so there are applications for the decoders, definitely. And for example, the 7-segment display decoder and traffic light. So the traffic light is a really good example for learning decoders. And we'll give you an example of using decoders to make a traffic light controller. To understand, the different patterns doesn't have to be one a certain pattern every time. Can be totally customizable. Whatever the customer need, it's you can change it. So the traffic lights. The traffic light controller, right? So for example, at the intersection of 2 roads, 2 streets, there are 3 traffic lights over here on this side and 3 traffic lights on the other side, right? And we name them green 1, yellow 1, red 1, green 2, yellow 2, red 2. And there's a specific pattern all these lights are following, and after they cycled all these cycles through all these patterns, they will come back and cycle all these patterns again. And so the job here we are going to do first is trying to figure out all the patterns, and then we can try to design a traffic light controller out of that pattern. Okay, so for example, we just list all these signal lines: G1, Y1, R1, G2, Y2, R2. And after we see how many patterns we have, then we can design how many inputs we need for the decoder. So in the very beginning, for example, you have green. This green light is on, and you want the other right light is on. You don't want 2 green lights to be on at the same time. So then there will be a traffic accident since all the cars are running on the 2 sides. Green and red at the beginning. So the next step will be you want to change the green one to yellow and keep this one to be red. So you are giving a warning to the cars on that street saying a red light will coming. So please adjust the speed or be ready to brake. Okay. And next will be red and red. Before you give a green to the other street, you want to make sure the cars over here stop first. Okay, to be sure it's safe. So red and red will be pretty short sometimes if you notice that when you are driving. And the next step will be this one will directly jump to green, and this one will still be red. And then for a while, so the cars has been running on this street for a while, and then there will be a warning created from there to let the cars to be ready to brake. And after that, so after give a warning, it's going to come back to this state again, right? And then this one will jump to green, and this one will stay in red. So it's just cycle back, okay? And you can find out there are a couple of redundant cases. If you see that, this case and this case are the same, right? And I believe there's another one has the same case as well. Okay. And I think we still need to give a logic to it to make it happen. But now let's see. Let's assume we have totally 7 cases. 1, 2, 3, 4, 5, 6, 7 cases. And we do need 3 bits. Since 3 binary bits will generate 8 combinations. Let's say A, B, C are 3 inputs to control all these patterns. So the places I keep blank will be zeros in the future. Okay, sorry about that. 0, 0, 0. Let's just use 0, 0, 0 to generate the first pattern. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. Right, from 0 to 6, so totally 7 patterns. And since we have so many outputs, we have to figure out one by one at one time, right? So let's see. So G1, what is G1? That will be A not B not C not, or A B C not. Okay, that's G1, and you can generate you can simplify this, and then do a or you can use K-map. If you can simplify this manually, that's fine. So for example, here I can take out C bar, so A B not or A B and C not, right? So I don't think you can simplify this further, but you can write it in this format. So it's going to be A X nor B and C not. So if you use a K-map, you only have two terms over here, so K-map won't actually simplify anything for you. So yeah, but for this case, you have four terms, so it's probably you can simplify further. But for this one, you couldn't do anything. You just list it, and then you have AB X nor X, right? And then nor, that's this term, and then you have C not and logic, right? So that's G1, the signal for G1. That's it. You still get the signal for G1 with green light to control this green light. You just connect this one to the light bulb, right? To the LED or something, ground it. You have a resistor here to protect it, so you can get a controller connect to the circuit. And you only have 3 inputs to control six pins. You're saving a lot of pins over there, right? So just keep going, okay? You got G1, you can get Y1, R1, G2, Y2, R2, right? Just keep going. You can get all these logic expressions and the circuit as well. So I'm going to show you one more case, which will use probably K-map. So let's take a look at this one. So which is R1, the red light. So what are they? Let's just put everything in the K-map, right? So A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now see where are they? Where are these ones? 0, 1, 0, right? 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. Okay, so you can simplify this, right? So what is that? So R1 equals to, which one is being toggled? C. So it's going to be A, B not. What is this? Which one is being toggled? C. Wait, is that C? Okay, it's C. So B. Finally, B is left over here. So it's going to be A, not B. It's actually A, XOR B will be R1. So if you have A and B, you just make XOR so you can get R1. That's it. Super simple. That's the signal for R1. Okay. You can keep going. You can get all these signals and the circuits for the signals. This will be on the homework for you guys to figure out what are they, and probably including a simulation. So when you simulate the file, you just do multiple times of simulation. You give a one pattern and simulate output. Just show all the signals on the output, and then do another run the simulate again, change the input signal and see the pattern, and just so on and so forth. So you can simulate all these cases. So there will be maybe a few different simulation work need to be done to verify the logic here, but I will let you guys to do it. And if there's any questions, welcome to send me an email or ask other people on the YouTube website underneath the video. You can have the comment area. You can ask other people or send me an email directly, or we can have a probably discussion session to run through this at the same time. But anyway, so this is application for decoder, and you can find out, you can design the pattern, depends on the real life. It doesn't have to be a certain pattern, but however, these are all the patterns you are going to use, and so that's why you need after you count how many patterns you will use, and then you can design how many inputs you need, how many bits for the input should be appropriate for this design. Okay. Thank you for watching. I'm going to see you in the next video.